Hello class, in this video we're going to be looking at the properties of ionic compounds. The learning intention of this video is for us to explore the physical structure of ionic compounds and to look at the physical properties of them as well. To start off this lesson, I'm going to be reviewing over the formation of ionic compounds. In our previous lesson, we said that ionic compounds form when two, single, or a group of atoms transfer electrons between each other. I've got two diagrams below that actually illustrate this process. In the very first diagram you can see over here, I've got humans to represent the electron transfer, but in this case of using electrons, we're actually showing the movement of the blankets between each individual. We can see that both Emily and Sarah are both unsatisfied at the beginning, and after Emily has actually transferred the blanket to Sarah, now both Emily and Sarah are satisfied. Similarly, in the other diagram that I have on the right hand side, we know that sodium has 1 valence electron, whereas chlorine has 7 valence electrons. In order for both of them to have a complete outer shell, what will happen is that sodium will transfer its electrons over to chlorine, and in doing so, it will therefore have an electron configuration similar to a noble gas. We say that the ions in an ionic bond are held together by these strong ionic bonds, which are characterized by these strong electrostatic forces of attraction, which results from this electron transfer process. The first thing that we're going to be looking at is the structure of ionic compounds. In the solid state, ionic compounds are said to have a crystal lattice structure. Now, you're probably already familiar with what the word lattice means, but in the case of ionic compounds, we also refer to as a crystal because it has this neat organized structure similarly to that of a metal. Okay, so it has a nice ordered grid-like arrangement as demonstrated by this diagram over here, and if you look closely, the individual layers have alternating anions and cations bound to it, and that's also represented by this diagram where the lines represent the ionic bonds. It is due to the strong electrostatic forces of attraction between the cations and anions that actually hold the atoms together to keep this crystalline structure. I want you to now have a go with answering these two multiple choice questions in the next 2 minutes. So the first question reads, which of the following gives the best explanation for the fact that sodium chloride is crystalline? If you guys have answered this correctly, the correct answer for this one over here is going to be B. Now, some of you guys might argue that A could be the answer, but A in this case is probably not going to be the best answer for this particular question over here. Part A reads, there is a strong electrostatic attraction between oppositely charged ions. Now, that is true, but that doesn't explain why does it have a crystal structure. Why does it have a nicely neat structure? The reason why it has a nice ordered structure is because they are arranged in this 3D arrangement. The second question reads, which of the following phrases would be used in a description for both the bonding in both metals and ionic salts? The answer to this question over here is going to be the strong electrostatic attraction. In metals, this occurs between the delocalized electrons and the metal cations, whereas in the ionic compounds, this occurs between the cations and the anions. We're now going to be looking at the properties of ionic compounds. So the physical properties of the ionic compounds can be explained in terms of its structure and bonding, which is why we had to look at the structure beforehand. And there are 4 main types of properties that you need to be able to explain by the end of this video. The first one is it's hard and brittle. The second property of ionic compounds is that they have a high melting point. The third property that you're going to be able to explain is that some of them are actually water soluble, but you're going to be looking into a lot more detail for this particular property next year. And the last property that you should be able to explain is that it has the capacity to conduct electricity when it's dissolved in water or when it's melted. So let's look at the first property. So ionic compounds have high melting point, and you can clearly see that by this particular table over here. So I've got 4 examples of ionic compounds, and notice that most of the melting points are within the thousands, okay? Now, remember, high melting point or melting point is a measure of the temperature going from a solid to a liquid, and because it's suggesting that you have a high melting point, that requires a lot of heat for it to actually convert between solids to a liquid. The reason why it does have a high melting point is because that the cations and the anions are packed tightly together in this nice lattice structure, and as a result of this, you will require a lot of thermal energy, which essentially means you need a high temperature to disrupt the bonds, and by disrupting the bonds, This allows for the individual ions to freely move so that it kind of looks like this particular diagram over here. So the next property that we're going to be looking at is why most ionic compounds are soluble. I like to emphasize the word most over here because there is a certain amount of ionic compounds that are unable to dissolve in water, but you're going to be looking into a lot more detail as to why that is in the following years. So the reason why that ionic compounds are able to dissolve in water is because the individual ions in the compound itself prefer to interact with the water molecules rather than interact with each other, okay? And it's due to this preference as to why the actual ions actually dissociate and therefore dissolve in water. So if you look at this image down below over here, we can see that the individual ions in the compound dissociate, and by dissociating, the water molecules that's present in the solution pretty much surrounds each of these ions and therefore interact with it, okay? And by dissociating, this also increases the surface area for them to actually interact as well. And this is also illustrated by this diagram over here. So in essence, all you really need to understand that in the presence of water, so therefore when it's in a solution, the individual ions in the ionic salt prefer to pretty much kick back with the H2O molecules rather than staying with each other when it's in the crystalline state. We're now going to be looking at the ability for ionic compounds to conduct electricity. Now, for ionic compounds, it can only conduct electricity at specific states, and it can only do so when it's either in the molten state or when it's in solution. So that means when it's dissolved in water. It is unable to conduct electricity when it's in the solid state. So, using your understanding of the two conditions for any substance to conduct electricity and the diagram below, can you see whether you can come up with a possible explanation as to why it is able to conduct electricity when it's in this state over here as opposed to the solid state? If you guys have answered this correctly, you would be able to explain that in the solid state, the cations and anions are in fixed positions in the nice 3D lattice structure. And because it's locked in place, it therefore doesn't have the capacity to conduct electricity as there's no mobile particles to carry the current. So as shown by this diagram over here, the cations and anions are locked in place. In contrast, when ionic compounds are dissolved or melted, we can see that the cations and anions over here are free to move around, and because of this, it therefore has the capacity to therefore carry an electrical current when it's placed in an electrical circuit. The last property of an ionic compound that we're going to be going through is that ionic compounds are brittle. Now, when we looked at metal bonding, we saw that metals actually deform their shape when a force has been applied, and the reason why they don't actually break apart is because they have the presence of these delocalized electrons, which prevent the actual metal cations from actually repelling from one another, which would therefore cause the actual substance to break apart. However, in an ionic compound, when a force has been applied, what actually happens is that you're actually disrupting the 3D lattice structure, and in doing so, you're actually shifting the layers. So in this diagram over here, on the left-hand side, this is an undisturbed 3D structure of an ionic compound. However, in the second image in the middle, when you apply a force, what actually happens is that you therefore cause the layers to slide, and by sliding these layers, you're now causing the actual like charges to become adjacent to one another. So therefore, they're now next door to each other. So as you can see, you've got the two cations next to each other right over here, and you've got the two anions next to each other over here. By having these like charges next door to each other, this introduces electrostatic forces of repulsion. And this is a force which causes the like charges to repel from one another. And because they're repelling from one another, this actually breaks the lattice structure. And as a result, that's the reason why they break apart. And you're probably already familiar with this when you have table salt in your actual pantry. So you probably will notice that when you've got a little clump of salt, you don't really require that much force for that to actually break apart. Before we end this video, let's review over the main properties of ionic compounds. We looked that they are hard, and the reason why they're hard is because you've got these cations and anions that are highly packed together due to these strong forces of electrostatic of attraction. We said that they're brittle is because that when you apply a force This causes the like charges to become next to each other, and therefore this causes electrostatic forces of repulsion. We said that they've got high melting point because of these strong electrostatic forces of attraction. So therefore you require high thermal energy to disrupt the bonds. They're also soluble in water for most of the ionic compounds, and the reason why that is because that the individual ions themselves prefer to hang out with the water molecules rather than hang out with the other ions. And lastly, they're able to conduct electricity in water or when melted because that they have mobile charged particles to therefore conduct electricity, whereas in the solid state, it's locked in these fixed positions and therefore unable to conduct electricity. To strengthen your understanding, what I'd like you to do is I'd like you to please answer the questions found on this particular Google form. So there are about 15 multiple choice questions on this. So I'd like you to do this to strengthen and consolidate your understanding. But also, once you've done that, I'd also like you to please answer these 4 short answer questions over here, because these are the questions that are commonly asked on your upcoming post test. This is the end of the video. Thank you guys for watching. I'll see you guys again in the next video. Bye.